Hello students, in today's lecture we will start on next module number 2 is inverse Laplace transform. So basically inverse Laplace transform is nothing but a inverse of a Laplace transform. As we have seen that Laplace transform is a function that transfers time domain to frequency domain, content from time domain to frequency domain. So in inverse Laplace transform we'll see we have to change a frequency domain to a time domain. So let's begin with, if f of t is given here, f of t is given to you and t is any positive number, then Laplace transform is defined as Laplace of f of t is equal to f of s. So function of t is transferred to function of s is nothing but the integral 0 to infinity e raised to minus st ft dt. In short, we may write Laplace of f of t is equal to f of s. So in as Laplace transform is the function which is both 1 1 and on 2, that is bijection. So we can write Laplace inverse f of s equal to f of t. So we have transferred this L to RHS and changing the sides. So we have written here Laplace inverse f of s equal to f of t. So for example, Laplace transform of t is equal to 1 upon s square. So that thing is we have seen in the last couple of lectures. So as Laplace of t is equal to 1 upon s square, then Laplace inverse 1 upon s square is equal to t. So we have to just replace the place of L. So Laplace inverse 1 upon s square equal to t. On the very next line we have another example, Laplace of 1 equal to 1 upon s. Okay, so from this we have Laplace inverse 1 upon s equal to 1. Okay, so as Laplace of t cube is equal to 3 factorial divided by s raised to 5, then Laplace inverse 1 upon s raised to 4 is t cube divided by 3 factorial is 6 here. Okay, so here we have t cube only, but in RHS 3 factorial divided by s raised to 4. So we may change this 3 factorial in place of this 3 factorial as 1 upon 3 factorial in the LHS. Then we should have L inverse 1 upon s raised to 4 equal to t cube divided by 3 factorial, which is 6. Okay, so very easy one. And so we list some formulas. Here we have 7 formula. So Laplace of t raised to n is equal to what? Gamma n plus 1 divided by s raised to n plus 1. So we are going to use this Laplace transform to list one another formula for 1 upon s raised to n plus 1. So L inverse 1 upon s raised to n plus 1 is nothing but t raised to n divided by gamma n plus 1, because here it is gamma n plus 1, but here the term gamma n plus 1 is missing. So the term is missing, that means this is transformed to RHS. Okay, so in the next, Laplace transform of e raised to at is equal to 1 upon s minus a. So we can write L inverse 1 upon s minus a equal to e raised to at. So easy one. Laplace transform of sin at is equal to a upon s square plus a square. Okay, as we have here a. So Laplace of sin at is equal to a divided by s square plus a square. But Laplace inverse of 1 upon s square plus a square. So here it is a missing. Therefore I have taken a here. So sin at divided by a. Are you getting my point? Similarly, for Laplace of cos at is equal to s upon s square plus a square is implies that Laplace inverse s divided by s square plus a square, which is equal to cos at. So we cannot take s outside this L inverse, because L inverse is a function of s here. So we are not going to take common. Now let's see another formula. Laplace of sin hyperbolic at is equal to a divided by, here it is a divided by a square minus a square, but Laplace inverse of 1 upon a square minus a square is equal to sin hyperbolic at divided by a. Laplace of cos hyperbolic at is equal to s divided by s square minus a square will imply Laplace inverse s divided by s square minus a square is equal to cos hyperbolic at. Last one, Laplace of 1 equal to 1 upon s, therefore L inverse 1 upon s is equal to 1. So we are going to use these 7 formulas to evaluate some problems. Let's see what is the problem here. So for example, we have L inverse 1 upon s minus a. What is that? L inverse s minus 2 equal to e raised to 2t, because this is from second property, Laplace inverse 1 upon s minus a is equal to e raised to at. So from this property we have Laplace inverse of 1 upon s minus a equal to e raised to 2t. So this is for the first one. So Laplace inverse 1 upon s plus 3 equal to e raised to minus 3t. Here we have negative sign, and instead of writing negative here we may write plus. So plus can be factorized as minus into minus. So therefore Laplace inverse 1 upon s minus of minus 3 is nothing but equal to e raised to minus 3t. Similarly for third one, Laplace inverse 1 upon s raised to 6 is nothing but Laplace inverse 1 over s raised to 5 plus 1. 6 is factored as 5 plus 1 equal to t raised to 5 divided by gamma t raised to 5. So second property, first property in the list we are using here. So is equal to t raised to 5 divided by factorial 5. Factorial 5 is nothing but 120, and therefore answer is t raised to 5 divided by 120. Now let's see Laplace inverse of 1 over s square plus 4. So this is nothing but Laplace inverse 1 upon s square plus 2 square. So this is nothing but sin 2t divided by 2 by using that formula. Laplace inverse s over s square plus 9 is nothing but Laplace inverse of s divided by s square plus 3 square, which is nothing but cos 3t. Okay. L inverse 2 divided by s square minus 9 equal to L inverse 2 divided by s square minus 3 square. But in the numerator we have 2. So we would like to adjust these 3 in the numerator also by multiplying and divide simultaneously throughout. So L inverse 2 by 3 into 3 divided by s square minus 3 square. Now 2 by 3 is constant and we may take outside. So 2 by 3 into L inverse 3 by s square minus 3 square. So this is nothing but 2 by 3 into sin hyperbolic 3t. Now let's see last example, L inverse 1 over s raised to 5 by 2. So this is nothing but L inverse 1 upon s raised to 3 by 2 plus 1, which is equal to t raised to 3 by 2 divided by gamma 3 by 2. So is nothing but t raised to 3 by 2 divided by gamma 5 by 2. But gamma 5 by 2 is nothing but 3 by 2 into 1 by 2 into root pi. So this is nothing but 4 by 3 t raised to 3 by 2 divided by root pi. Okay. Now let's see next one. Properties of Laplace inverse transform. So first property is shifting property. As we have seen a shifting property in Laplace transform, so similar kind of property is here. So we may take first Laplace shifting property of Laplace transform. If Laplace of f of t is equal to f of s, then Laplace of e raised to at f of t is equal to f of s minus a. Okay. So similarly, Laplace inverse f of s is equal to t f of t, then Laplace inverse f of s minus a is equal to e raised to at into f of t. So similar kind of property is here. So we have this property to be used in the near future examples. So if Laplace inverse f of s equal to f of t, then Laplace inverse f of s minus a is equal to e raised to at into f of t. So we are going to evaluate one example by using this property. So evaluate Laplace inverse 1 upon s plus 2 bracket cube By shifting property, L inverse 1 upon S plus 2 bracket cube is equal to e raised to 2t, because here it is plus 2, it is so therefore it is minus 2t, therefore is equal to e raised to minus 2t into L inverse 1 upon S cube. So this S plus 2 is transformed to S only by shifting property and taking e raised to minus 2t common, sorry, outside. So e raised to minus 2t into L inverse 1 upon S cube is nothing but e raised to minus 2t into t square by 2 factorial, which is 2. So let's see another example. Evaluate L inverse of S divided by S square plus 2S plus 2. Okay. So we have seen a numerator and denominator in this, so fractional function of S. Now to solve this type of problems, we factorize denominator if possible. Otherwise, we make denominator as a perfect square. So here we have S square plus 2S plus 2 as a denominator, and by simplifying it turns, it is not possible to factorize. Okay, S square plus 2S plus 1. So I'd like to write S square plus 2S plus 2 as S square plus 2S plus 1 plus 1. So simply write this 2 as 1 plus 1. So we have L inverse S divided by S square plus 2S plus 1 plus 1. So furtherly it will be S plus 1 bracket square plus 1. Okay, so L inverse S divided by S plus 1 bracket square plus 1. But in the denominator there is only S, so we can add and subtract 1 simultaneously. L inverse S plus 1 minus 1 divided by S square, S plus 1 square plus 1 is nothing but 1 square. Now using linearity property in L inverse, so L inverse of S plus 1 divided by S plus 1 square plus 1 square minus L inverse of 1 over S plus 1 square plus 1 square. Okay. Now let's see by shifting property. Here we have using shifting property. Kindly note it. So here it is in the denominator and the numerator S plus 1 term is occurred. So e raised to minus t into L inverse. So this S plus 1 is transformed to S only, and this S plus 1 is transformed to S only. So e raised to minus t into L inverse S divided by S square plus 1 square minus e raised to t into L inverse 1 over S square plus 1 square. This is equal to e raised to minus t into cos t, because L inverse of S over S square plus 1 square is nothing but cos t, and 1 over and here it is L inverse 1 upon S square plus 1 is nothing but sin t. So if we take e raised to minus t common throughout, so we have e raised to minus t into bracket cos t minus sin t. So final answer is Laplace inverse of S divided by S square plus 2S plus 2 is equal to e raised to minus t into cos t minus sin t. Okay, so this is the final answer, and this is the one of example in the property of Laplace inverse Laplace transform. So we may see some another properties and examples in the future lectures. So let me stop here.